So now, we're going to do a step-by-step build of the LM358 op amp, wired as a voltage follower, right there. So the voltage we give to the plus input, that's non-inverting, will be the same at the output, thanks to the negative feedback. You can see the output is being fed directly back to the inverting input, right there. And one thing to always keep in mind with op amps is that the output changes, so that whatever the input voltage is, the output voltage will be the same. That's the main thing. When the output is fed directly back to the inverting input, then it's the same voltage that you got at the non-inverting input. And there's a lot of different ways you can take advantage of that properties, but this is one of the simplest ones. So I have the pin layout right there. I actually got the LM358 I'm going to use out of this kit. So usually I just look right at this kit. We have inputs we're not using. We're not going to use that op amp over there. And I believe you want to wire that one as a voltage follower as well, putting the plus input to ground, even though there's no load. But always check the data sheet for whatever integrated circuit you're using for what you should do with unused inputs. And so in any case, we're going to use the one on the left right there. I have it written down, and it is on the board. So you may or may not have noticed this shared a spot with the NE555. So I usually have to look at the part number, and I believe it will be that way. And I can see it with my bare eye. There we go. LM358. And then it says P on there. That usually means that it's improved from the original. But they're all probably going to be P now. They're probably all going to be approved. They made it change. And that's just letting you know it's not the original, basically. So yeah, I guess we'll put that on the board first. And lately I've been putting the trim pot on the board. So yeah, we plug it in, and already you can see the output, top left pin, directly back to the inverting input, -1. Pay close attention to schematics though. Sometimes the plus is put above the minus. Maybe it's easier to draw or whatever. But on the physical component, at least for the LM358 op amp, the minus is always above the plus. So you gotta make sure you wire it right. So always review this integrated circuit. Don't assume that what's above on the schematic is also above on the component. So yeah, that's really it for the voltage follower, other than our signal. So I'm going to use a 10,000 ohm trim pot. So there's a 10,000 ohm resistor basically between that pin and that pin, and then this pin here is a wiper that slides up and down along there. So you get a voltage divider that you can adjust it anywhere up to the full positive supply, down to the full negative supply, 0 volts down there, 9 volts we're going to work with in this circuit right there. We can go anywhere in between those 2 points. This trim pot though, which is short for trimmer potentiometer, I mentioned before that's the potentiometer symbol. Trimmer potentiometer is just a small potentiometer. It's kind of meant to be built into a product or something where you set like a voltage and then, you know, basically leave it. Whereas potentiometers are bigger. They're made for being used a lot. But they're a lot more expensive and stuff, and trim pots probably work for you. So in any case, let's get back to the circuit. We're getting that to the non-inverting input. These inputs don't let current in or out, which is good because the trim pot will change its voltage. If current has to be provided, then it's going to drop the voltage, and if current's being pushed into it, it's going to raise the voltage at the trim pot. So you just want something to look at the voltage and then work from there, and that's what the trim pot's really good at. Comparators can't work as voltage followers, but they just look at the voltage and respond to it. So I'm going to cover the component on there because we're a little bit limited space. So again, we're using 9 volts. So I got a red LED here. We're going to put the long lead, the anode, to the output. Short lead, the cathode, we're going to go up 1 spot so that I don't have to pull these apart. And then, so that's upside down from how I normally wire it. But the main thing is the long lead, the anode, will be towards the more positive side when the output is high, and it will light up because this resistor is going to head to ground right there. So that's how I want to wire it. We could wire it up so it lights up, when the output's low, put the resistor to the positive supply, but we're not going to. We're going to stick with this voltage follower circuit. So the power supply is off. Always wire this up while the power is off. You know, you can remove the alligator clip too to be safe. If it's going to a battery, remove the alligator clip. And then after you verify everything is wired right, reattach it so that you apply power with the battery. But I just hit the button to turn the power supply on. And now you're going to see that the LED gets brighter as I turn the trim pot up. So that may be enough for you now, but we might as well get out the multimeter and see how accurate this is. I think it's going to be pretty accurate, definitely a lot more accurate than when we used the bipolar junction transistors. We cascaded an NPN and a PNP to eliminate their offsets, but it was still off a little bit. I think this one will be more accurate, especially if we get rid of the load. So now I got the multimeter. I'm going to set it to measure voltage. All I got to do is V right there. It's an auto ranging meter. It does the rest unless I want to change it to alternating current. But we're just going to measure DC here. Don't have to move the red probe for anything but high current with this particular meter. Other meters you may have to move it. So let's, speaking of move the lamp into a better spot right there. Now I am not going to push on stuff with the probes. Instead, I took these alligator clips right there and I pinched the ends onto the other end of one of these breadboard jumpers right there. So the other end looks just like this, but now there's an alligator clip on it. I can clip that to the probe and then plug it into the board so that I'm not pushing on stuff. And so yeah, just clipped it there and we plugged it in. Gonna do the same thing with the positive, or the red probe I should say. So it's not always more positive, so I try not to say positive, but any case, it's the voltage in relationship to this. So we consider this 0 volts. Now we got 3.3 something volts above 0 right there, positive voltage. On the schematic you can see I say +9 because it's 9 volts higher than our ground symbol right there, which is 0 volts. And ground in this case is the negative supply. So I can go down to 0 volts since I have, well, I mean 0 volts, so negative supply. But since we're using 9 volts, I can go up to 9 volts, and you see the LED gets brighter. And we do have connections and stuff where we're going to lose a little bit of that 9 volts. So just be aware of that. And we could look at what the rail voltage is compared to the trim pot, and it looks like yeah, the connections for the jumpers and everything, we're losing a little bit more. This isn't the highest quality breadboard, and with breadboards, wherever you have connections, you're going to be losing a little bit of voltage. It has a little bit of resistance, but always be aware of that. So, in any case, we got at the non-inverting input 8.84 volts. So, hopefully, we have the exact same voltage at the output, but I can't guarantee that, so we will take a look. So what I say, I think I said 8.89. Oh yeah. So I wasn't thinking about this. The output actually does not get to the full supply voltage, and it's going to be a little bit worse when we have to provide current. So the full voltage is something you got to keep in mind. You're not going to get that full voltage. I should have thought of that. I haven't made this circuit in a long time. So what we're going to do is let's go to 6 volts. See how well we're doing when we get 6 volts at the output. And so we're 5.8. I'm not going to stretch this out too long. That's close enough. So 5.95. Let's see. That's the output. Let's see what the trim pot is right there. And yeah, really, really close right there. Now it's basically spot on. So because it's drifting a little bit. But we were slightly lower than what we had before. Now we're slightly higher than what we had at the output. So it's basically the same right there. Maybe drifting just a little bit. But there you can see. So again, this is a voltage follower. The output voltage is going to follow what the input voltage is because of the negative feedback. That's the main thing when it's the op amp. So that's a straight jumper going from the output to the inverting input. It should be, you know, exactly the same voltage right there. And so that is how it operates. And it's doing pretty good. We got that load. I thought maybe I would have to get rid of the load and looks like it did change a little bit, 5.99. Let's see what we got there. Yeah, about the same right there, for whatever reason. And I don't know, maybe the load did change what the output or the trim pot voltage is as well. Yeah, it looks like it does. For some reason, it's drawing current, and so maybe it's changing the rail voltage by a little bit or something, affecting the trim pot voltage and whatnot. So again, those are all things you could look into in great detail if you really wanted to. Try to figure out exactly why you get discrepancies. But for the most part, we could see we got whatever voltage we set with the trim pot to the non-inverting input. The output is providing that same voltage thanks to the negative feedback, even with the load right there. So I thought the load might complicate things a little bit, but doesn't look like so does so far. These op amps aren't for providing a lot of power. I think you might be lucky to get 20 milliamps of current. Maybe you can get a little bit more. Maybe it'll struggle to get 20 milliamps. I'm not sure. So I haven't done that testing a lot, and with different LM358s. But these are not power op amps. So there's power op amps that can provide a lot more power, and they may be even worse at getting to, in this case, the positive supply voltage. As we saw, we fell short of the positive supply voltage. I'm going to try to turn it up to 9, and you're going to see that it's like 7.23, even without the load, and it's doing better without the load. That's to be expected. We can get to 0 volts, so these connect to 0 volts pretty well. I got the trim pot to 0. We can check if that still holds with the load. I think it will be just a speck worse, but I think we'll still stay really close to 0 volts when yeah, I gotta put this to the positive supply right there. And now it's going to the long lead, the anode of the LED. I turned it around, and so yeah, that's the output voltage. I'm surprised it's not going to 0 volts. So that is something to keep in mind. Let's try without the load. Yeah, it's 0 volts without the load, but the load, yeah, threw it off a lot more than I expected. That's kind of interesting. So we would again have to do something about that. It should not should have dropped to 0 volts. So we can raise it now, and you can see as we get a higher voltage here, there's less voltage across the LED, so it turns off. But in any case, this went on long enough, so I hope you enjoyed. Make sure you check out one of the other videos I posted on the screen, and check out the links down below. They all help out a lot. I'll see you in the next video.